Welcome to today's FDTD Go 16 Applications webinar. Today we're pleased to have Frank Elsheimer from the Columbia, South Carolina WFO leading our discussion for today. First, a few notes before we begin. All these are recorded, and if you're interested in viewing the recording of these, they're on this particular webpage, which can be found off the Visit webpage. Also, a call for speakers. If you're interested in leading a future webinar, let us know. Either myself, Dan Bicus, or Scott Lindstrom, and our email addresses are listed at the bottom. Just a few protocols to go over before we begin. Frank will have about 20 minutes for his presentation. If there is any question, you can either send it via the GoTo chat, or right after Frank is done speaking, we'll have a question and answer period over the phone. We'll be done within half hour, so after Frank discusses, we'll have up to a 10-minute time for any questions. Remember, do not press hold, and also remember to mute when you're not speaking. So at this point, I will turn it over to Frank.
Thank you, Dan. Good afternoon, everybody in eastern part of the country. Good morning in the western part, and if you're listening in Guam, God bless you. But we're going to talk a little bit today about using Go 16 for a convective event over the southeastern United States. It's going to be a scenario-based presentation. It's given on a typical summer convective day in the southeastern United States, in this case July 7th. I'm going to give a brief meteorological overview, but we really want to spend most of our time looking at the GOES products that we have available in the GOES imagery. So we're going to talk about the cloud and moisture imagery, probably what most of us are used to looking at, although I may add in a couple of bands that maybe you don't look at quite as frequently. Channel difference products, where we're subtracting two channels from each other to get some usable information. I'm going to talk briefly about baseline products and show specifically one example of a baseline product that is useful in this situation. And we're going to talk about RGBs. Again, I'm not going to get too detailed because of the time constraints we have, but I do want to show you the benefit of using RGBs for this particular convective situation. So here's what the surface map looked like at 15Z on July 7, 2017, and it's a very typical summertime map for the southeast. It's hot, temperatures in the low 90s already along the east coast, dew points in the mid-70s, and there's no sign of a front anywhere to be had. So really a pretty typical hot and steamy situation for the southeast. Here's a look at the 500 millibar flow. Generally, you've got a ridge in the western part of the country with a trough in the east. But if you look at the 500 millibar winds, they're pretty much on the weak side over the deep south. A little bit westerly, a little bit stronger as you get a little bit into North Carolina. But the strongest winds are really coming down on the backside of the trough to the upper Midwest. And this can be reflected pretty well in the SPC convective outlook for that day. You see the biggest area of emphasis is the enhanced, where that wind is going to come down from mid-levels and interact with the cold front, and there is a slight risk around that. But down in the area that we're looking at in the Carolinas, there is a marginal risk with SPC giving a nod to the fact that even 25 knots of wind at 500 millibars, given the expected surface and mixed instability, could cause some issues. So now let's get into some of the satellite imagery here. The first thing I'm going to show is the red band, band 2, the visible band, and of course this has got the highest spatial resolution of all the bands, half kilometers. So let's take a look. I'm going to loop it through once, and then it'll start to loop through again. And this is a loop from roughly 1330Z to a little bit after 16Z, which would be a little bit after noon local time. And I really want you to pay attention to a couple of different areas, in the green and in the yellow. In the green, you'll notice that the cumulus looks a little more agitated. We've got a little bit of a hint of some TCU in there even, and it's pretty good indication that this is probably going to be the first area to go for convection as we move into the afternoon. On the other hand, the area in the yellowish to orangish oval, there's a lot less activity going on. So as a forecaster sitting here at noontime on this given day, you're thinking, all right, the first areas of convection I'm going to be concerned about, let's say you're doing an afternoon update, maybe your TAF forecast, where convection might bother air traffic for the afternoon. You kind of get a little idea of the potential timing of this convection. Another thing that you'll notice here that I don't have circled is it looks like a little bit of a shortwave there along the northern Georgia and western North Carolina border. That can also play a role as we get later in the day. Now, of course, as a forecaster, one of the things I'm also concerned with is the potential for severe weather. If you remember, there was a marginal risk from SPC. As we get into the summer months, one of the things we look for here is later ignition time for the convection. That will allow for better surface-based instability to develop. And it also might be a hint that there's dry air at some level that could play a role in the potential for microbursts with any convection later in the day. So let's start looking at a couple of these other bands that might help us determine better what exactly is going on. So one of the new bands with GO 16, and one of my favorite bands, is the low-level water vapor band. It's band 10, 7.3 microns. And it helps to show you an idea of the potential water vapor in the lower parts of the atmosphere, lower than we were able to see in previous GO series. Here, our weighting function probably is a maximum somewhere around 600 millibars or so. So if you look in the green, there's definitely more moisture in the green at this level. So you're talking lower. Low might be a little bit of a misnomer because we're not looking at like 850 millibars, but in the 600 millibar, roughly give or take 100 millibars based on the shape of the weighting function, we definitely see there's a little bit more moisture back in western Georgia and eastern Alabama, as well as in southern South Carolina. But if you get up into central South Carolina and eastern Georgia, you notice it's a little bit drier in the mid-levels. And so right away that sends off a flag for us that, all right, we might have a little bit better enhancement to the wind threat with these thunderstorms as we go through the afternoon, assuming there's sufficient moisture for convection, which is what we're expecting. Now, if we look instead at the upper level water vapor, here our weighting function is going to maximize out at about, say, 350 millibars or so. So we're up there quite a ways. And it shows quite a bit of moisture pretty much everywhere at this level. There's not a whole lot of signature in my mind that you can pick out looking at this. You might argue there's a little bit less in the areas that are in the orange circle there, but I don't think, it's not certainly something when you're looking at this that would pop out to you to say that there's an issue. So looking at that lower level water vapor band was really a benefit in this case. So now let's look at a channel difference. And we're going to look specifically at the difference between the clean IR long wave, which is band 13, and the dirty long wave, which is band 15. Let me explain a little while we're looking at these channel differences. First of all, to start with, explain that this is just a simple subtraction of two bands, and probably the best known in the Weather Service example of this is what we call the fog and low cloud channel difference, where you're subtracting the IR from or shortwave IR. It can be in either direction. And this really helps at night figuring out areas where you're getting fog and low clouds. You lose it during the day because of the reflectivity in the 3.9, but at night it helps for locating that fog and low clouds. Well, today, the example I'm going to show you is a little different. It's what we call the split window difference, and it's the difference between two of these infrared channels. And the reason why we're looking at that is for an indication of how much low-level water vapor we have. The 12.3 micron band is modestly sensitive to water vapor in the lower parts of the atmosphere, whereas the 10.3 band has very little sensitivity to water vapor. So when we subtract these two, we have a little bit of an inference of the moisture at low levels. So let's take a look and see what this product looks like. Here I had to change the color to a black so you could see it, otherwise the orange or the yellowish band wouldn't show up. But pretty much in all these areas of interest, there is a fair amount of moisture by looking at the reds, the warmer colors here. You could obviously some purples where you're getting already the clouds and the convection. I think what's actually easier to notice is the front back over northern Alabama and up through eastern Tennessee. The areas behind that are much more yellow, and the areas ahead of it are more red. So you definitely have more low-level moisture, according to the split window difference, available to the south and east of that area in the areas that we're really concentrating on right now. So let me briefly talk about baseline products. This is the whole list of baseline products that we're going to be getting with the GO 16 and GOES F once it gets up there. It would take way too long to talk about all these things in a short 20-minute presentation. So the one I'm going to concentrate on for the purposes of this scenario is the total precipitable water product. This is the total precipitable water product only from GOES. There are some advantages to using this product. You get 5-minute updates on the CONUS scale. So unlike some of the blended products, you get this a much more frequent update, essentially every time you would get a CONUS scale image. And we have found it relatively reliable for exact values within 0.1 or 0.2, depending on the situation. But honestly, the gradients are just as important as the actual readings, as you'll see in the example I'm about to show. Now, there is one disadvantage, is that it is not calculated in cloudy regions, because we don't have the correct bands to see down through the clouds on the GOES. That's more a polar orbiter LEO. So what you can use in that place is these blended TPW products that combine GOES and polar orbiting information. The downside is that the latency is not nearly as nice. But for this example, I am going to show you what we can see on the 5-minute update with the TPW. Now, one thing you'll notice in this loop, first of all, is that so that I don't have a lot of black spots on the screen, what I've done is overlaid the visible satellite imagery so that it fills up and you can kind of see where the clouds actually are that cause it not to be calculated. But again, let's look at these areas here that we've been looking at now throughout this event. And you notice that the values are a little bit lower in that area of the orange oval, and they're a little bit higher in the area of the green oval, indicating that our full layer of PW is a little bit lower in that area from central South Carolina into eastern Georgia. And that is to be expected based on what we saw in the lower level water vapor with the indication of drier air at those semi-lower levels in that specific spot. So it's not a surprise that we see this reflected in the baseline product. So what happened? Here's the rest of the story. And to do that, we're going to show you some RGBs. So just a very brief explanation. RGBs essentially are consolidating information from different spectral channels into a single product. You get more information than one channel alone, and you have different RGB recipes that allow features to stand out of interest. You have RGB recipes that help you determine convection, smoke and fire, ash and dust, air mass characteristics, and certainly several more. And we'll probably discover more as we have more and more chance to look at the GOES 16 data. So there are really two types of RGBs that we look at right now. A simple RGB, which is just looking at individual channels that are combined, and then an advanced where we're looking at things such as taking channel differences and using them in the recipe for RGBs. So this first one I'm going to show you is an advanced one. It's called an Mass RGB. And this is adapted from the EUMETSAT folks who have been using this since about 2009 or so with their series of satellites. There's a lot on this table. I'm not going to get too deep into it, but essentially this particular RGB allows us to help identify jet streams, stratospheric air intrusions, certainly useful in the wintertime, short waves, air mass types, and upper level moisture boundaries, just to name a few. So let's take a look at a loop. Again, here are the areas, but I'm not going to leave the levels on so it doesn't get too cluttered on the screen. And you get kind of an idea of where the lower values are in there. But to let you in on a little secret, I am what they call color vision deficient, or what's more commonly known as colorblind. And so a lot of this, I can't see anything. Your RGB is my WTF. So I need to find a way to make this stand out a little more for my eyesight. So one thing I like to do with this RGB is overlay on top of it the colder cloud tops from the 10.3 or the band 13. And to me, in this way, I can see the convective towers develop, and they really stand out for me a little bit more than they do otherwise with just the regular RGB. That may be something of benefit for you all, or you may be able to see it just as easily in the Mass RGB as it stands. But one thing that's for certain is that you could see that area of slightly less moisture in the Mass RGB over our area of interest. And now at this point, as we get towards the end of the day, you can see the convection firing in that area. So now let's look at another RGB. This is a simple water vapor RGB. You can see it's just 3 different channels. And this can be used for low-level moisture return in the absence of clouds, cyclone features, convective initiation, and many wave features. So let's take a look through the event of what this looks like. And again, here's the areas of interest. And I think you can see there's a little bit more green at the beginning of this in the area where the orange oval is. And then shortly after that, you can really see the convection really developing in that area where it waited a little bit longer to go. I know I'm starting to get a little short on time here. So let me just run through what the visible band looked like so you get a feel for how the entire day went from originally we saw the Q, and now we can see the entire set of events as the convection really got active, likely due to a combination of the shortwave as well as the near storm environment that those storms were moving into. Of course, there's a lot of convection going on back in Alabama and Mississippi as well, due to a number of different factors. You've got some Gulf sea breeze interaction there, and you've got outflow interaction going on as well. But even there, you can see the towers, and really the tallest towers are across from northern Georgia across into northeastern South Carolina and even southeastern North Carolina. So what happened? Here are the reports from that particular day. And if you notice, I'll put the circle up that we've been looking at. That was the area that had the highest concentration of severe wind reports. So looking at these different aspects of the GOES, looking at the individual channels, looking at the channel differences, looking at the RGBs, as well as the baseline product, PW, all kind of gave us an idea, without even looking at models, of how that afternoon was going to evolve in the area in terms of convection. And here's a time-lapse that was taken near the Columbia Airport as one of those storms was moving in late in the afternoon. Always like seeing a little time-lapse there. Hopefully you all can see it well, too. So, takeaways. The GOES 16 and S can help determine the mesoscale environment supportive of convective development or suppression. You've got the cloud moisture imagery channel differences, baseline products, and RGBs, all useful tools in both diagnosing the current conditions, and nearcasting convective initiation. And finally, the proper combining of images and color curves can give additional context beyond what you would get from a single image. So are there any questions?
Frank, this is Scott. That was great, and I just have a comment on the split window difference field that you showed.
Yes.
If you can back up to that.
Uh-huh.
One of the other important things about that, in addition to moisture, is the skin temperature. So you will have noticed, if you looked at that the ocean had a much different temperature than the land. And I'm kind of doubtful that the moisture distribution had that big discontinuity right there at the ocean front. So just keep that in mind when you're looking at the at the split window difference too. So you'll notice as the land gets warmer and warmer, the ocean is not getting warmer and warmer. That's telling you something about the temperature of the surface, not necessarily the moisture. So it's something to keep in mind when you're trying to interpret the split window difference.
Thanks. I appreciate you adding that in, Scott.
Was you showed a visible toward the end? Was that supposed to be animating? Because I wasn't seeing that. I couldn't tell if that was a hiccup or.
I'll show it again.
Yeah, I saw a still image, and that was it. It seemed like there was a time there where things kind of stopped moving.
I can get back there.
Sorry for making you jump around.
Okay, I see it animating on my screen.
And I see it animating now, but before I just saw a still image.
Okay.
So.
Any other questions or comments for Frank?
Hi, Frank. That was a great presentation. Thanks. We have a question. The split window, the difference product that you were talking about, that doesn't appear to be on our menu. Should it be on our menu, or is there an easy way to derive that product from what we have available?
No, it should be on the menu. Let me take a look.
Yeah, it's on my menu under Channel Differences. Go 16, Channel Differences.
Okay, yeah, we checked our menu here, and it's not here, so we probably need to update something, I guess. I just wanted to double-check that.
Yeah, it's labeled as moisture on there. I'm not sure why it's labeled that, but it is labeled as moisture.
Okay, so it's labeled as moisture, not split window. Is that correct?
Right, and next to it on the EWIPS menu, it'll say 10.3 minus 12.3.
All righty then. Thanks. We found it.
Okay.
Okay, any other questions or comments?
This is Dan Lindsay. I'll also point out regarding that difference that it's also useful for detecting blowing dust when values get into the negative values, which I think on the color table are getting into sort of a brown color. So for those of you who are out west or where sometimes you get blowing dust, use that for that application as well. Same for volcanic ash, but that's not so much of an issue usually over the continental U.S.
Thank you, Dan.
Any more questions or comments? Okay, hearing none, we want to thank Frank for leading our discussion today, and this will be posted, the video on the Visit web pages pretty soon, and we'll have our next webinar in 2 weeks. Thanks, everybody, and have a great day.